Ultrasound waves are sound waves with frequency higher than 20,000 Hz or 20 kHz. This is above the range that humans can hear. Like ordinary sound wave, ultrasound waves travel through materials such as air, liquids, and solids. However, because of their high frequency, they can be used for many special applications. Do you know that the development of ultrasound technology began after the discovery of the piezoelectric effect by Pierre and Jacques Curie in the 1880s? In the early 90s, ultrasound was used in sonar systems to detect objects underwater. Later, scientists developed ultrasound technology for medical imaging and industrial purpose, making it an important tool in modern science. Ultrasound is an important technology in modern science because it allows us to obtain information without damaging the object being studied. It is safe, non-invasive, and provides real-time results. Ultrasound is widely used in scientific research, medical diagnosis, and engineering applications due to its accuracy and reliability. Its ability to detect, measure, and image objects make it a valuable tool in many fields of science and technology. Ultrasound waves have many important applications in different fields. In medicine, they are used to monitor pregnancies and examine internal organs. In industry, ultrasound helps detect cracks and defects in materials without causing damage. In underwater exploration, sonar technology uses ultrasound waves to measure ocean depth and locate underwater objects. This application shows how ultrasound has become an important tool in modern science and technology.
Okay, now let's explore the scientific instrument and application technology behind medical ultrasound imaging. Medical ultrasound imaging is diagnostic technology that uses high-frequency sound waves, typically between 1 and 20 MHz, to produce image to of structure inside the human body. It is widely used because it is safe, non-invasive, and do not use harmful ionizing radiation. The operation of an ultrasound system begins with piezoelectric effect. Inside the transducer are piezoelectric crystals that can convert electrical energy into mechanical vibration. When the electrical pulses are applied to this crystal, they vibrate and generate using ultrasound waves that travel through the body. As the ultrasound waves propagate through the different tissue and organs, they encounter boundaries with different acoustic properties. At this boundary, part of it is reflected back as the echo, while the remaining portion continues traveling deeper into body. The transducer acts as a receiver. The returning echo causes the piezoelectric effect to vibrate again, converting the mechanical energy back into electrical signal. Therefore, the transducer performs two important functions: transmitting ultrasound waves and receiving reflected echo. The received signals are usually very weak. Therefore, the ultrasound machine using signal processing technique to improve signal quality. The echo are amplified, filtered to remove unwanted noise, and converted into digital data. A computer then analyzes the signal and calculates the position of the reflecting structure based on the time taken for the echo to return. Next, the system performs image formatting. Thousands of echoes are processed every second to reconstruct a real-time image. Strong echo appear brighter on the display, while the weaker echo appear darker. This enables doctors to distinguish between the different tissue and organs accurately. One important application of this technology is pregnancy monitoring. Ultrasound allows doctors to observe fetal growth, determine the baby position, and detect possible abnormalities without exposing the mother fetus or the radiation. Another major application of echocardiography. which is used to examine and structure function of the heart. Using Doppler ultrasound, doctor can also measure the speed and direction of blood flow to identify. In addition, ultrasound is commonly used to examine organs such as liver, kidney, gallbladder, pancreas, and thyroid gland. It will help to detect abnormality, include cyst, tumor, and stone.
Imagine being able to see a baby before it is born, or detect objects deep in the ocean where light cannot reach, or even park your cars without seeing what's behind you. All of these are possible made by one powerful concept, which is ultrasound. Ultrasound uses high-frequency sound waves to detect and visualize objects that are invisible to human eye. And today, it plays a crucial role in both medical and everyday technologies. I'm going to explain the applications of ultrasound waves. One of the most important applications of ultrasound waves is in medical imaging, especially during pregnancy without having a surgery or radiation. A device called a transducer sends high-frequency sound waves into the body using piezoelectric crystals that convert electrical energy into sound waves. These waves travel through tissues and reflected when they meet boundaries between different structures such as muscle or bone. The reflected waves, called echoes, return to the transducer. The system measures the time taken for the echoes to come back and uses this to calculate the distance of internal structures. A computer then converts this data into a real-time image where brighter areas show strongest reflections. As a result, ultrasound allows doctors to safely monitor the body, detect abnormalities, and observe fetal development without harmful radiation. But ultrasound waves is not only limited to the human body. In the ocean, ultrasound waves is used in sonar technology. Sonar stands for sound, navigation, and ranging, and is used in the oceans to detect objects underwater. Ships and submarines send out ultrasound pulses into the water. When the waves hit objects like fish or other vessels, they are reflected back as echoes. Besides large-scale applications, ultrasound waves is also used in our daily lives. One of the common use of ultrasound waves is in car parking sensors. The sensor sends out sound waves toward nearby objects. When the waves hit an obstacle, they are reflected back as echoes. The system measures the time taken for the echo to return and calculates the distance using this information. As the car gets closer to an object, the warning sounds become faster, helping the driver judge distance and avoid collisions.
Now, I want to talk about the potential benefits and challenges. First, it is safe and non-ionizing. Unlike X-ray and CT scans, ultrasound does not use ionizing radiation. Therefore, it is generally considered safe for patients, including pregnant women and developing fetus. Second, it is real-time imaging. Ultrasound provides real-time image, allowing doctors to observe the movement of organs, tissues, and blood flow instantly during the examinations. Third, non-invasive procedure. Most ultrasound examinations are non-invasive and painless, which is reducing discomfort and risk for patients. Fourth, cost-effective. Ultrasound equipment is generally less expensive than MRI and CT scanners, which is making it more accessible in hospitals and clinics. Last but not least, wide range of applications. Ultrasound is used in various fields such as medical diagnosis, physical therapy, underwater imaging, industrial inspection, and robotics. Now, the challenges of ultrasound technology. First, the operator dependency. The quality and accuracy of ultrasound image depend heavily on the skill and experience of the operator. Second, limited penetration through bone and air. Ultrasound waves cannot easily pass through bone or air-filled structures, which is making it difficult to image certain body parts such as the lungs and brain. Third, lower image resolution. Compared to CT and MRI, ultrasound may produce lower resolution image, especially for deep tissues. For image artifacts, reflection, shadows, and other imaging artifacts can sometimes affect the image quality and lead to misinterpretation. Okay, now I want to talk about the future developments and innovations of ultrasound. First, AI-assisted ultrasound. AI technology is being integrated into ultrasound systems to improve image analysis, assist diagnosis, and reduce operator dependency. Second, portable handheld ultrasound devices. Modern ultrasound machines are becoming smaller and more portable, which is allowing healthcare professionals to perform examinations in remote areas and emergency situations. Third, 3D and 4D ultrasound imaging. Advanced 3D and 4D ultrasound technologies can provide more detailed image and real-time visualization and improving diagnostic accuracy. 4. Wireless ultrasound systems. Wireless ultrasound systems do not require cables, which making them more easier to use and move during the examinations. Lastly, integration with telemedicine. With telemedicine, ultrasound image can be shared with specialists in different locations, which allowing them to assist in diagnosis remotely.
In conclusion, ultrasound is a very important technology that uses high-frequency sound waves for imaging and measurement across many fields, especially in medical, industry, and underwater exploration. It is a safe, non-invasive, and highly effective method that helps us to obtain information that cannot be seen with naked eye. With continuous technological advancements, ultrasound is becoming more accurate, faster, and more accessible. Because of this, it is expected to play an even greater and more significant role in future science and technological development.
The heart of most ultrasound systems is a device called a transducer, which uses an array of piezoelectric crystals. A piezoelectric crystal vibrates when an electric signal is applied, producing high-frequency sound pressure waves, which we call ultrasound. More importantly, this type of crystal can also work in reverse. It can produce electrical signals when it detects high-frequency sound pressure waves. When a transducer directs ultrasound waves into the body, they pass right through the skin and into the internal anatomy. As the waves encounter tissues with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal. This happens more than 1,000 times a second. Returning echoes are converted to electric signals, which a computer converts into points of brightness on the image, corresponding to the anatomic position and the strength of the reflecting echoes. A medical transducer contains a large array of crystals, which allow it to make a series of image lines that, together, form a complete image frame, called a sonogram. In addition, all the crystals are repeatedly activated many times in such a way that a complete image frame is formed around 20 times per second, so that real-time motion is displayed in the ultrasound image.